Today we're going to review what we can learn from the algebra of the first and second derivatives and what that tells us about the graph. So how you can use, we've used charts and tables last year, how we can use that to interpret what would be happening on a graph. So we're going to look at the first and second derivative tests for the different extrema. We're talking about concavity, and we're going to define points of inflection. So this again should be pretty much a review lesson for you. So we define a critical point as being something where f prime changes sign. Okay, that is the definition of a critical point. It can happen at a soft curve or it can happen at a cusp. Either way, we have the idea of changing from a positive to a negative or a positive to a negative in terms of slope. It can happen when it's either equal to 0, the derivative, or it's undefined. So both of those are candidates for a critical point. If it's a minimum, then the change is happening in such a way where we're changing from a negative to a positive, either at a corner or at on the bottom of a parabola. We're changing from negative to positive. Again, you're looking at both equal to 0 or equal to undefined. And when we talk about undefined, we talk about the slope being 1 over 0. And I would recommend when you're thinking about the slope being equal to 0 that you're thinking about it being 0 over 1. Those are two important things. But again, the important part is changing sign. If there is no change in sign, then you do not have an extreme value. So if the slope is positive and continues to be positive, even if the first derivative is equal to 0, that is no extrema. Or if the slope is negative and continues to be negative, even if it is undefined, that is no extrema. The key is the change in the sign. So you can look at a continuous function and have places which do have undefined or 0 derivatives, but no extrema exists. And so you would need to justify why either an extrema does or does not exist. So in terms of slope. Okay, so identifying any absolute extrema, we're going to take our derivative. We're going to set our derivative both equal to 0 and undefined. So our derivative will be 3x squared minus 27. We will set that equal to 0. We factor. So x squared minus 9 equals 0, which implies that x has the solutions of plus or minus 3. When we set the derivative f prime equal to 1 over 0, the implication of that is we have no additional solutions. All right, so then we're going to set up the intervals where x is less than 3, x is between negative 3 and 3, and x is greater than 3. And on those intervals, we test our values to see what the extremas will be. So I'm going to test negative 4. And when I put negative 4 into the derivative, I get a positive value. I'm going to test 0. When I put 0 in, I get a negative value. And I'm going to test positive 4, gives me a positive value again. So f of x has a max value at x equals negative 3 because f prime of x changes. So from positive to negative. Don't say f prime changes from increasing to decreasing. F prime is not changing from increasing to decreasing. F itself is changing from increasing to decreasing, but f prime is not. F prime is changing nature from positive to negative. And then we would say and a min value at x equals positive 3. And then because f prime changes from negative to positive. All right, you guys were really good at that last year. Okay, as we get to concavity, we are looking at how the derivative itself is changing. So remember, the derivative tells us how the function is changing. The second derivative tells us how the derivative is changing, and we call that concavity. And so we would say in a concave down section, you kind of phrase it this way. It's increasing, which means the graph itself is going up, but it's increasing at a decreasing rate. That means it's getting less steep. It is still continuing to go up, so which means it is increasing, but it's increasing at a decreasing rate, as opposed to quadrant 2 here. It is also an increasing, but it's increasing at an increasing rate, which means it continues to get steeper as it goes. As it goes up, it is getting steeper. And so our concavities can be described a couple different ways. You can describe concave up when y prime, the derivative, is increasing, or concave down if the derivative is decreasing. That's the increasing or decreasing rate. You can also use the second derivative as a measure of that, either positive second derivative or a negative second derivative, to indicate concave up versus concave down. This also is a way to justify the local maximum. If you use your first derivative and set it equal to 0, and I would add or 1 over 0 for both of those. And then you add a secondary thing by checking the concavity, then you can defend the position of a local maximum or a local minimum. And so we kind of picture that. If we say, okay, this graph has a derivative of 0 and a concavity that's negative. And so that leads to the definition of a local max. Or vice versa. Okay, if you have maybe a graph that looks like this, and so you have a derivative that is 0, but a concavity that is positive, that's the definition of a local min. So you can either use the justification of a change using only the first derivative, or you can reference the concavity along with the first derivative and also come up with a valid definition. So let's use that method to find the local extreme values. So I can do that without making a chart. I can go to f prime, which would be 3x squared minus 6. Setting that equal to 0 leaves me with 2 solutions, plus or minus rad 2. And then I can go to f double prime of x, which gives me 6x. So I can say f prime at rad 2 is 0. F double prime at rad 2 is positive. That implies that x equals rad 2 is a local min. That the combination of those two things, having a 0 derivative and having positive concavity, would be a local min. I can say f prime of negative rad 2 is also equal to 0, and f double prime of negative rad 2 is negative. That implies that x equals negative rad 2 is a local max. So you can check it without having to make a chart. So it's up to you. You kind of have to evaluate each situation. Is the chart going to be easier factoring the derivative and checking numbers, or is it going to be quicker to find the second derivative and justify the locality of your extreme values that way? Up to you. So to summarize, you have to state clearly that the derivative is either 0 or undefined. That is a no-brainer. That is true for both of them. You have to state that. You won't get full points in the rubric. Then you may either do one of the following. You may either mention a change in f prime, and that change, if we're going to be a minimum, from negative to positive. Or you can show, if it's a minimum, we need to show positive concavity. Either one of those is a legitimate justification when you want to justify. So for a maximum, you want to mention a change in f prime from positive to negative, or you can show, so a maximum comes from negative concavity. Okay, either of those will be sufficient as a justification. Now, if you want to talk about changing in the second derivative, this is how we justify a point of inflection. So a point of inflection, you must show that f double prime equals 0 or 1 over 0, and mention or show a change in f double prime of any kind. So it doesn't matter if it's positive to negative or negative to positive, either way, we're getting a change in concavity. So those count as a point of inflection. So there's two parts to that, just like there are with extreme values. So if we want to find all points of inflection for this kind of fun-looking exponential graph. So we want to look at the first derivative. So first derivative is going to be 2e to the negative x squared times the chain rule, and the chain rule is negative 2x. So I'm looking at negative 4x times e to the negative x squared. Then we want to find the second derivative because we're focusing on points of inflection. So this is going to require me to think about the product rule. So I'll have e to the negative x squared times negative 4 as the derivative, plus negative 4x times e to the negative x squared times the chain rule of negative 2x. So cleaning all that up, negative 4e to the negative x squared plus 8x squared e to the negative x squared. Factoring that, we recognize that we can take out a, we could take out a 4 and an e to the negative x squared. That leaves me with negative 1 plus 2x squared. And I would set that equal to 0. Solving will give me 4e to the negative x squared being set equal to 0. And since exponentials never touch the x-axis, that doesn't produce any additional solutions. And then negative 1 plus 2x squared equals 0. That leads me to x being plus or minus square root of a half. So those are my potential points of inflection. To prove that, I would need to check the second derivative. So I'd need to have all x values that were less than the square root of negative 1/2, the negative square, and then negative square root of 1/2 up to positive, and then greater than the positive. And then we're checking the second derivative. So I'll pick something that's clearly less than that. I'm going to say like -10 or something. I mean, just something that's so far negative. But when I plug it into my derivative, I always find it's easiest to plug it into the factored form. So I'm going to put -10 there. -10, I'll plug it in and I'll square it, which will give me positive 100. And so clearly that's going to give me a positive value. Okay, if I put in 0 as being the middle term, again, I'll plug 0 in right there. That will simplify that factor to -1, and putting 0 in the other x squared is just going to give me 1, so I've got a negative number. And then the same thing will happen here. So I've demonstrated a change in nature of the second derivative. So I do have the value, the x coordinates at least, of the points of inflection. But a point means I need to know the x and the y. So I'm going to have a point of inflection to be negative rad half. And then if I plug that into the original function and square it, that'll give me 2e to the negative half. And then my other point of inflection would be positive rad 1/2. And then squaring that also gives me the same value. Okay. In this last example, we'll use our calculator to find points of inflection. And so in your y1, you're going to put the square root of x and x plus 3. In your y2, you'll be using your math 8. And so most of you will have math 8 being set up, and we want to reference the derivative of y1. And then we want to say for all x's, that's for all real numbers. So you want to specify, so I think you're going to have to enter that we want our x, this is relative to x. You have to put in y1 and you have to put this in. You're going to use the vars option to get that y1 in there, and then isolate, make sure you go to your y vars and then function. And then in y2, excuse me, y3, you're going to reference the derivative of what's in y2, and you'll do that for all x's. And then what you want to do before you hit graph, you want to make sure to turn on and turn off the different equal signs. So you should turn off, remember, put your cursor right on the equal signs and hit enter, so that only the equal sign for the third one is highlighted. When you get to your zoom 6, so that's just a standard window, you're going to have a graph that's going to come up and it's going to cross the x-axis and then barely go into quadrant 1. And so that solution right there is indicating a change in concavity, where the graph is changing from negative values to positive values. Those values indicate the concavity, changing from negative concavity to positive concavity. That's what it means. And so we want to focus in on what that value is right there. So we'll calculate that 0, and that turns out to be, mine gives me lots of 1. So as we round that, we would say that x is 1 is the point of inflection, the x value at least of the point of inflection. We'll plug that back into the original equation, and so we get the point 1, 4 is the point of inflection. And we say because the values of y2, of the second derivative of y double prime, change nature. So we're using our calculator to help us. You could do this one algebraically as well. You would need the product rule to find the first derivative, and then you end up needing the quotient rule to find the second derivative. So certainly possible to find it, but if it's not grayed out, then go ahead and use your calculator.